think the rate that it's become part of the Linux kernel and part of distributions really reflects how in high regards and it's an important technology just to the broad community as well. So pass it over to Josh. Thank you.
Thank you, Lloyd. So I'd like to get started. Today I'm going to talk to you about how you can store virtual machines in Cinder with Ceph and Ceph's block device, RBD. So first I'd like to give you a little bit of an overview of Ceph, where we come from, why Ceph was created. So if you look at the current state of storage, you can buy these gigantic storage appliances that you get your first petabyte, and it costs some bazillion number of dollars from some storage vendor, but then you're kind of stuck. What happens when you want to get your next petabyte, when you want to grow? Well, you're going to probably have to go back to the same vendor, and you're stuck with the same price, with the same old kind of system. You can't easily upgrade a single component of it. You can't add more RAM. And this is kind of odd because these systems are actually like computers these days. They're actually regular servers running Linux or some other common sort of operating system underneath. But you can't actually interact with them. When you encounter problems, or when you want to use something that they don't provide directly, there's really nowhere for you to go. You have to go directly to that single vendor. You're kind of locked in. So that's kind of the genesis of Ceph. In addition, we noticed that when you have lots of these little spinning Rust record players in production, and you have millions and millions of them, they tend to fail quite often. If you have about 1 million disks, you'll expect to see about 55 disks fail every single day. That means you're going to have huge replacement rates. And when you're replacing things by buying a whole petabyte at once, it just doesn't scale. So that is where Ceph comes from. Ceph is designed for scalability, having no single point of failure. And it's entirely based on software, so you don't have to keep being locked into one single hardware vendor. And you can always upgrade and tweak it yourself. And it's designed to be self-managing as well. So whenever some part of the system goes down, when disks fail, and you're having hundreds or tens of disks fail every single day, you don't want to have to go and manually replace those yourself. You want a storage system that can handle that. Additionally, we like the system to be open source because we really believe that open source is the best way to grow a storage solution. It's really the best way to, in fact, the entire future of the storage industry lies in open source. Today, we're stuck with these giant proprietary chunks of storage, but these can be they're really difficult to use and hard to grow. But open source really lets anyone take ownership of their storage and use their storage to its full potential. So here's a basic outline of Ceph. There are several different components. The most basic layer underlying everything is Rados, the object store. On top of that, there are several different interfaces you can interact with the object store. There's a POSIX-compliant file system. At the very top, there's a block device called RBD. There's a gateway, which provides a RESTful interface to the object store. Or there's just a direct library access. So let's talk a bit about how this object store works. On each storage node, you'll have many disks. And on top of each disk, you'll have some kind of file system. Just a regular Linux file system like ext4, Btrfs, or XFS, anything that supports extended attributes. And running on top of these file systems, you'll have an object storage daemon, or OSD. And each of these OSDs stores data in its local file system, but presents those files as objects. So when you go to interact with the cluster, you're talking through some native Ceph client, and you're interacting with all of the storage servers potentially at once. So you can leverage the full power of your cluster from a single application. So there are two basic types of daemons in Ceph. There are monitors, which maintain basic cluster status, like which nodes are up or down, how many nodes there are, where the data should be placed at this time. But they're not in the data path. They just maintain maintain who is in the cluster. The object storage daemons, they're the ones that actually store the data and serve it. And they serve it directly to the clients. So clients will connect to the OSDs, write to them, have the data replicated by the OSDs automatically. And the OSDs deal with failure themselves, so they're intelligent. They detect failure among themselves with the gossip protocol, and they re-replicate data as needed to ensure strong consistency. So whenever something goes down, the OSDs will notice and determine exactly where data needs to go, so that it can be replicated to the proper number of replicas. So one problem that comes up with a gigantic distributed storage system when you have many, many servers is, how do you find your data? Well, one way to do it is to write it down somewhere in a lookup table. And every time your client goes to access the data, it has to know that data, go to the lookup table and see where the data is. Well, that's fine for small systems, but as you grow, maintaining this lookup table and making it consistent maintaining that consistent view throughout the system becomes more and more expensive. So one common thing that's done is just consistent hashing, which is where you say, okay, if it starts with F, my data goes in that bucket, and it's stored on these object storage daemons. And that is great, unless you have a whole bunch of objects that start with F. Then you have nothing else stored anywhere else. So this is what Ceph decided on, something called crush. In order to place an object in Ceph, you take the object name, you hash it, and that becomes part of a placement group. And then you add as an input to the crush function this placement group, a cluster state, which your nodes are up or in, and a set of policies that define where your data is placed, like how many times replicated, and whether it's replicated across different racks or rows. So you put in an object name into crush, it gets hashed into a PG, and then these PGs, or placement groups, get placed on different OSDs. Now you'll notice that they're distributed pseudo-randomly. It's not like this OSD is an exact copy of this OSD. This placement group is a copy of this one, and this red guy over here is a copy of this one. So these aren't mirrored pairs or anything like that. One of the great benefits of crush is that because it's a pseudo-random placement algorithm that's stable, whenever you add more storage or remove a node, it migrates the minimal amount of data. So the placement algorithm is stable in that if a node goes down, the existing set of nodes will stay the same, but the one node that went down will be subtracted. And if you add a new node, the existing mappings will stay the same as well, with some small amount of rebalancing. Now, crush is pretty powerful. It allows you to define a variety of rules for how your data is placed. You can store one replica on really fast disks and use that to serve reads from. And you can store 3 other replicas on slower disks, where just for durability and reliability. So when a client goes to interact with the cluster, how does it know where objects are? Well, as you recall, monitors are maintaining this cluster state, and this includes a map of the cluster, what OSDs currently exist, and what the crush rules are. So that defines how to place data, and how to find data in the cluster. If a node goes down, for example, this OSD dies, the OSDs will notice and automatically re-replicate the placement groups. So this one was storing a yellow placement group and a red placement group. And the red placement group is re-replicated over here, and the yellow placement group is re-replicated over here in parallel. So recovery time is very short, because the entire cluster can recover in parallel from a given node going down. It's not like RAID, where you have to wait for an entire disk's worth of data to be shuffled onto one other disk. It's many disks in parallel recovering the state of the cluster, and making sure the data is up to date with the right number of copies. So when this OSD goes down, and the client goes to look for it, it will get a new updated map of the cluster based on the gossip protocol that the object storage daemons use to distribute it, and say, oh, now this data is stored on these OSDs. I'll go to them to grab that data. And if that node comes back up, because crush is stable, the data will go back to the original place it was. So that was Rados, the underlying storage system for everything in Ceph. It provides strong consistency, and it's self-healing, and deals with all the failure and recovery automatically, so upper level layers don't have to worry about it. To interact with this Rados cluster, there's a few different methods. One is to use librados, which is a native library with bindings in C, C++, Python, Ruby, basically any language you can think of. Talk directly to all of the storage nodes. This also lets you leverage actual computing power on the storage nodes yourself. You can actually define custom functions that you can run on top of objects. For example, you could store an image as an object and run a function that generates a thumbnail of it on the storage node itself. In addition to these custom functions, you can actually define transactional semantics. So you can do a transaction where you do a read, modify, write cycle and implement all kinds of fancy things like locking or counters that only increment if a certain value is set to this number. Basically anything you want. On top of this low-level object abstraction, there's also a higher-level interface, the Rados gateway. The gateway sits on top of librados and exports a RESTful API that's compatible with S3 and Swift. So you can take your existing S3 or Swift clients and just run it against a Ceph cluster with Rados gateways in the way. You can have load balancers in front of them, and you can have a whole cluster of Rados gateways cooperatively serving these objects with strong consistency. So you always have read after write consistency. Another layer, which is right on top of Rados, a relatively thin one, is called RBD, or the Rados block device. And this is what's really useful for storing virtual machines. So the Rados block device sits on top of the Rados as well, but it has its own library called librd. And this is linked to hypervisors like QEMU, so that they can access the cluster directly. They don't have to go through the kernel. They can just talk directly to all the storage nodes and get data for a guest they're running. And because they're talking to any of the storage nodes and they can access the storage nodes from anywhere, this allows the virtual machine to become independent of the host, so you can migrate it from one host to another. There's another way to access it, which is through a kernel module, which has been upstream in the Linux kernel since 2.6.37. And that lets you expose the block device directly on the host, just like a regular Linux block device. So these block devices are thin provisioned, and they're striped across Rados objects, so you get the performance of many, many spindles in one virtual disk. They also support advanced features like snapshots and cloning. And they let you decouple the host, or the virtual machine you're running, from the underlying storage it's using. Now suppose you want to run many virtual machines, which is usually the case. You don't ever want to run really one virtual machine that often. Usually you're running hundreds. What if you want to have all these virtual machines booting off of a similar image? Well, with a thin provisioned virtual block device, like the Rados block device, you can do this with a copy on write cloning mechanism. So say you have your base image here, which defines, like, say it's Ubuntu 12.04, and it takes up 144 objects. You can create an instantaneous copy of it, which takes up 0 extra space. Then, when your virtual machine starts writing to this new block device, it will do a copy on write. So if you write to this block, it'll go back here, read it, and copy it up to the new block device. And if in the read side, the client goes to read from this block device, it notices that that block up there doesn't exist, for example. It has to go read from the parent. So how does this all relate to OpenStack? Well, one of the things that's been a problem in OpenStack is that there's no easy way to use block devices or advanced storage systems to back virtual machines. This is a picture of how virtual machines are typically created by default. You have Nova requesting an entire image from Glance over HTTP, downloading the image, storing it on a local disk, and then running the instance from that image on the local disk. Now, this is okay, but there's lots of benefits to be had from using a block storage system like Ceph. For one thing, block devices are persistent by default in OpenStack, so you can have a more familiar experience where you actually have data that, like in a database, that stays around when your instance dies. You can even shut down an instance and start up somewhere else. It also allows you to independently scale computational power and storage. You can have a giant storage network and a few compute nodes that leverage tons and tons of IOPS from that storage, or you can have many, many compute nodes accessing a small storage cluster because you don't need that much performance. You also get the ability to take advantage of efficient snapshots. Instead of using an object storage system to back up a running virtual machine from a local image, you can just use native snapshot support in the storage system without very much extra space overhead or time. In addition, you could have different types of storage available to a compute node. You could have some fast, some slow, some replicated many times, and some only replicated once, depending on what the use case. You don't get that benefit of those kinds of options with just using local storage. So in Folsom, we've changed the picture a bit. Instead of, prior to Folsom, there was really no way to populate data onto a block device. You had to kind of manually attach it to an instance, put data there yourself, and only then could you boot from it. Now with Folsom, Cinder has learned how to talk to Glance, and Glance can respond back with a full copy of the data directly to Cinder, and Cinder can then write it to the backend storage system. And that's great. Now you can easily boot from that kind of volume. But it still involves a large copy of data from Glance to Cinder, which is really not necessary. There's been a storage backend in Glance since Diablo to store images or templates for VMs inside of Rados block devices. So in Folsom, if you have your Glance backed by the Rados block device, and you have your Cinder creating a new block device from that same image, Cinder will talk to Glance and ask it, where is this stored? And if Glance says, oh, this is stored in the same cluster that you're already using, Cinder can just create a copy and write clone of that existing image. And that allows you to have tons of new machines virtually almost instantly, using no extra storage and no extra time to copy all that data. This isn't quite perfect yet. There's still some enhancements to be made to make it more usable in Grizzly. Right now, this is you can do this from the command line or using the API directly, but it's not integrated into Horizon yet. So you can't do this from the GUI dashboard. But we have high hopes that this kind of use case where you're actually using an external system, storage system, to back your virtual machines will become much more common quite soon. Are there any questions? So the question was, if you change your crush rules and you say you add some more fast storage, how does the crush system change the existing data? It really depends on what kind of change you're making to your crush rules. So one of the details I didn't go into yet was that Ceph has different pools of storage, and each pool has an associated crush rule set with it. So if you're adding a new pool of fast storage, that wouldn't change any existing data. If you're just adding some more nodes to an existing pool, it's just like adding any other nodes. Of course itself doesn't have a notion of fast or slow, although you can give different nodes different weights within a given pool. Go ahead. Yes. By default, they're 4 megabytes, but it's a configurable size. So you can make them 512K if you want more write performance for very small writes. Or you can make them larger if you're doing much larger I/O. There were some questions over here. Right now, we don't. We might in the future, but we haven't really fully decided what the best way to do that would be. The question was, for the Rados gateway, do we interface with Keystone? And right now we don't, and we're not sure what the best way to do that would be. In terms of I/O, so this is all going over the network, so you can actually use the existing network tools to limit and throttle a virtual machine's access. You can also, QEMU has integrated throttling for block devices itself, so you can use that as well. There are Ceph limits in addition to that, but usually you want to throttle the entire VM as opposed to an individual disk. Yeah, so how you do that, you can configure however you like. It's actually been integrated with OpenStack since Cactus. So you've been able to back your VMs with it since Cactus. What's new in Folsom is that it's actually easy to populate these VMs with an image. In the past, you had to actually manually copy data onto it, a volume, before you could boot from it. And now that's an automatic process. Yeah, so the question was, because Ceph is striping a block device over many objects with a block device, doesn't that turn sequential read-to-write into random read-to-write? And that's generally true for reads. It does turn reads into random reads. But for writes, the OSDs actually have a journaling, which they write out sequentially. And so that keeps writes sequential. So you might have your journal on a faster disk for if you want to have fast writes, whereas you have your main data store on a spinning disk. So for reads, there's actually client-side caching for the block device integrated with QEMU. So that tends to help read performance quite a bit as well. It really depends on what kind of I/O your application is doing. If you're doing large I/O, that will help a lot. If you're just doing 4K reads, that won't really help because you're hitting the same object. The question was, where do you put the copy and write exception metadata for the inversion volumes? So this is one of the things in Ceph. We tend to avoid lookup tables. So we don't actually store an index of which blocks have been copied up or which haven't. Instead, we can optimistically, if we're reading, we try to read from the child object, and if it doesn't exist, we then go back to the parent. Soon we'll have an optimization for that where we actually cache which objects don't exist. And in the write case, you can optimistically write to the child, assuming that the object already exists. And if it doesn't, then you have to fall back to doing the copy and write. it's all handled in the librd layer, so the layer that lets you access block devices. So when we say, the question was, we say this is a shared block device, how do we arrange when multiple hosts are trying to access it? So when I say a shared block device, I don't mean that multiple hosts will be writing to it simultaneously. It's more like a physical disk, in that you can layer like another clustered file system on top of it if you actually want to have multiple hosts accessing it and writing to it simultaneously. What I'm trying to get across by saying it's shared is that you can access it from any individual server. It's not tied to a single host. So I guess the question is whether we're doing mirroring or not. So yeah, so when I say there's no mirroring, I mean an entire server is not, or an entire OSD is not an exact mirror of any other OSD, but the individual placement groups themselves are mirrored. The question is how we tested it in large scale, and does it roll over? And there's lots and lots of stuff going on. Well, the answer is that we've gotten tested many things at large scale. The Rados block device is the next one. Currently, DreamHost is running its Dream Object Service directly off of the Rados gateway, and its soon to be launched compute service is running off of Rados block devices. I'm not sure what the number of VMs are. So right now, the question was, is there a way to have replicas that are offsite? And right now in Ceph, all replication within a cluster is synchronous. What you can do is you can create snapshots of block devices and create clones of them in an offsite pool, or you just copy them directly. And you can perform a flatten operation, which is basically performs the copy on write for all of the blocks. And that'll let you migrate data from one pool to an offsite pool, for example. Okay. So the question was, what's the rate mix between metadata servers and OSDs? And we didn't really talk about metadata servers, but they're only necessary if you're using the Ceph POSIX file system, which we don't recommend for production use yet. The rest of the layers are ready for production, but the Ceph file system itself needs more quality assurance and testing. In general, though, it depends on your workload. If you have lots and lots of metadata operations, you're going to need more metadata servers, but it's really independent. You can scale the metadata servers independently of your OSDs. The metadata servers are not in the data path there. in Cinder, nothing has changed. That's still the case. It probably will change in Grizzly. To repeat the question for the video, there's a column in the MySQL table for Cinder that stores which host block device it has been attached to, or is created on, is being exported from. Yeah. I'm sorry, could you repeat the question? The question is whether the file system is involved in the snapshotting and the copying. No, this is all about the block device itself. So you can snapshot block devices, and you can create clones of block devices. That optimization is all about creating a block device from an existing block device when you're storing your glance images on a block device. It's not necessarily crazy. The question was whether it's crazy to set up your Ceph cluster where you have your OSDs on your hypervisors. And it really depends on what you're using exactly. If you use it, it's not recommended that you use a kernel client that way because you run into an unavoidable deadlock whenever you have a kernel client and user space daemon. NFS is the same problem with loopback mounts. But in general, as long as you have some extra headroom for the OSDs in terms of their memory use, you'll be fine. What is the requirement for memory for the OSDs? Generally, they use around 200 megabytes when they're just serving normal data. During recovery, when they're copying data around, they may use up to a gigabyte or two. Yes, to be explicit, the QEMU and the RBD stuff is all in user space. So that's fine to run on the same host as your OSDs. Yeah. So the question was what's going on with the images being backed by volumes. And the answer is that Glance actually has had a backend to store these images on RBD, on the block devices, since Diablo. So Glance itself knows how to write to a block device. So the question is, how does the replication work? And it works by the client writing to what's called the primary, or the first in OSD in a group, and that OSD will write in parallel to the other secondaries, and then the client will get the response when all those writes are complete. Yeah. So the question is, what is the monitor quorum, and what happens when it's lost? So the monitors maintain the cluster state, and they require a quorum, which means a majority of them to be available and connected to each other in order to make progress. That's so that Ceph can survive network partitions. If you have a network partition where there's no quorum, so there's you have 5 monitors, and you have 2 in one place, 2 over here, and 1 over here, and none of these groups can talk to each other. Then your OSDs will still continue serving data, but they can't get any new cluster maps because the monitors can't generate new cluster maps without being in a quorum. So existing virtual machines will still continue to run, but if if OSDs fail in that state, they won't get the new cluster map noticing that those OSDs have failed. So that's why you generally want to have your monitors spread across failure domains, so you can always have a majority of them around. So the question is, if you have a split lane and you have writes happening, what happens afterwards? And the monitors themselves aren't involved in the data path, but when they're updating the cluster map and the cluster state, only those who form the quorum have the ability to update that state. The other ones know that they're not in part of a quorum, and so they don't perform any writes. Okay, so the question is, how does the caching layer deal with syncs when the host is only writing, say, 4K? And there's a couple of things. One is that the fact that it's split into 4 megabyte chunks doesn't mean that you're always writing 4 megabyte chunks. Radius is actually a more powerful object store than like S3, for example. You can write any offset in an object, any length, and update anything in it. So think of 4K will only actually write out 4K to the disk, and the cache is well behaved. So it respects any flush requests that come in from the guest. If you don't want to respect flush requests, you can turn that, add the unsafe option to QEMU, which makes it not send any flushes down to the block device. Thank you very much.
Will be about 10 minutes till the next session is in here, and it's on heat orchestration within the cloud.